so we're going to do a little bit of theory stuff today, building off of the rectangle things that we talked about before break. Okay, so you remember we defined a integral, also known as an antiderivative, as the area under the curve of some graph. And so we're going to play off of that a little bit and introduce something called a Riemann sum, and then actually start calculating the numerical values of those areas. But we're going to take little baby steps here. So we start with quite a bit of theory, and then once we get done with the theory, we can move on to application. Okay, so we're going to introduce or talk about what a Riemann sum is. It's a little bit different than the rectangles. We're going to use definite integrals. This is probably one of the more crucial things that we'll cover with integrals. Then we'll talk about the properties. This is pretty boring. And then we're going to do some geometry to find calculus problems. So we're going to use geometry, very simple, to find calculus problems. If you can find the area of a circle, if you can find the area of a triangle, if you can find the area of a rectangle, you'll be golden. Okay? Can you do that? Then you're golden. Okay, so this looks a little bit different than what we did before break. You'll recall before break, we set up rectangles underneath curves that all had the same width. We calculated that delta x, right? B minus a divided by n. The starting point, the ending point divided by the number of rectangles you want gives you the width of each rectangle. So in all those examples that we did, we were looking at rectangles that had a width of 1 or a half, but it was consistent across the whole thing. So along comes this guy named Riemann. I don't remember his first name, to be honest. And he asks a simple question. Why do the rectangles have to be the same size? And you can see by looking at that graph, it doesn't necessarily do anything for us. But in the long term, it's going to allow us to get a more accurate answer. And that's our bottom line goal here, is to get as accurate an answer as possible. By the way, if I add up the yellow, blue, green, and rectangle, will I have an overestimate or an underestimate? Over. Okay, good. Just making sure we're all on the same page here. So Riemann asks a simple question. Why do they have to be the same width? Right? And this, let's get some notation out of the way first. We got this big scary thing. I know, it's a good one, right? Yeah. Anybody know what that big letter is? That is a sigma. Anybody know what it does? It is in a fraternity, yes. In fact, it was in my fraternity, Sigma Tau Gamma. Thank you very much. It's a sum up. Beautiful. Thank you, Dexter. So this looks scary, but I'll explain it to you very easily. Delta x is the width of a rectangle. Okay, now forget about the picture there. Think about the rectangles we did before break. Delta x is the width of a rectangle. F of c is the height of any individual rectangle. Doesn't matter which one, just pick one. So f of ci times delta x will be the area of one triangle. And then as Dexter mentioned, the sigma adds all those rectangles up. You've done this already. This is just a weird way of writing it. Okay, so width of one rectangle, the height of one rectangle, add them all up, and you've got the approximation of the area under the curve. So, like I said, Riemann asks a simple question. Why do they have to be the same size? So think about it this way, and I'm going to ask some silly questions, but it's relevant. Which rectangle is biggest? Sorry, let me rephrase that. Which rectangle is widest? The green. So we're all in agreement, yes? Okay, now, here's the concept part. If I start shrinking all those rectangles at the same rate, which rectangle will disappear first? Then which one disappears? Then which one? And we're left with? And we take that down to 0 and that disappears. One of the things we talked about at break was, how do we get a more accurate answer for the area under the curve? And there were two ways. Increase the number of rectangles or decrease the width of the rectangles. You with me? Okay, so if I decrease all those rectangles at the same rate, the only one that's going to be left at the end is the green one, the biggest one. Does that make sense? Any questions? Okay, good. So then we get into all this fun stuff. Riemann said, let's take this thing called the partition. The partition would be the interval. How many, we're going from where to where, in other words. The norm is the big fat rectangle. In our case, it's the green one. Hence the reason largest width is written in green. And then he fires up a bunch of notation. If we take the limit as the norm goes to 0, in other words, if I take the limit as the green rectangle goes to 0, by the time that goes to 0, all the others have gone to 0. If the width of the rectangles goes to 0, then how many rectangles will I have? If the width of the rectangles goes to 0, how many rectangles will I have? Infinity. Very good. Is that okay? No? Someone's ringing? Let's see. Maybe we can extend a warranty.
Wait, but
You can't be bashful. You just gotta start yelling, phone ringing, phone ringing, and then I'll come running over.
What if it's mine though? Like that's what I'm confused. Like,
Well, how are you gonna know if it's yours?
because I can see the light go.
Okay. Well, then I'll know. If Katie's yelling,
Then I don't wanna tell
phone
you,
ringing, and you're
I'll
sitting there
yell
quietly,
it.
I can pretty much determine it's your phone, and we're gonna have some fun.
Wait, but I'm confused about the infinity. Rectangle. Sorry,
Oh, I thought you were still talking phones, like infinity. What's an
I-
infinity phone? So you're confused about infinity?
Yeah.
Well, remember we talked about making the answer as accurate as possible. We want really skinny rectangles.
Yeah.
In order for that to happen, the number of rectangles has to get bigger. Because I'm only going to put X number of rectangles in this space, right? So if I take this space from 0 to 1, right now I've got 4 rectangles. If I make these skinnier in order to go from 0 to 1, I need more rectangles. Okay, and that's an inverse relationship. If I increase the number of rectangles, they have to get skinnier. If they're skinnier, I have to have more rectangles.
Okay.
So the theory is if the width of the rectangles gets very, very small down to 0, then I have an infinite number of rectangles.
Oh.
If I have an infinite number of rectangles, then my answer becomes exact. Because it now just becomes a bunch of segments stacked next to each other. And you have an infinite number of them. That's our ultimate goal. We want the exact value of the area under the curve. Adding up the yellow, blue, green, and rectangle right now is not an exact answer. It's an approximate answer. Like we talked about, it's an overestimate because there's a bunch of stuff above it. Okay. So, Riemann says, well, what if we make the biggest rectangle go down to 0? And again, I'm going to repeat what I said before. If the biggest rectangle goes down to 0, then all the rectangles have gone to 0. And we have a perfect answer because we have an infinite number of rectangles. Are we okay with this? Now, I know you're panicking. You're thinking we're going to do limits again, right? Yeah, we're not. And we're not going to really work with that sigma stuff that much. I just wanted you to be exposed to it so you knew what it was, because occasionally those kind of weird sigma questions pop up on the AP test. What are we going to do? Well, we're going to continue talking about some fundamental theorem of calculus, which is what we're going to eventually get to. But we're going to start by tying in what we did before break with this stuff. Okay? The thing we're doing now is called the definite integral. So we did an indefinite integral. And it's important that you understand the difference between the two. In the indefinite integral, if I take a function and I take an indefinite integral, I get another function. We've done that ad nauseum, right? The integral of x squared is 1/3 x to the third power. Okay? Taking the integral of a function gives you another function. A definite integral, however, is a numerical answer. It's the exact area under the curve. We approximated that with rectangles. Eventually, we're going to work up to getting the exact answers. That's going to take a little bit of work, though. So, this is what we get. I know it looks pretty scary, but all we care about is the right-hand side of that equation. The left-hand side is all the Riemann stuff. Okay, make the rectangles go down to 0, therefore you have an infinite number of rectangles, and you have the exact area. The right-hand side says, oh yeah, that stuff on the left-hand side is great, but why can't we just do the right-hand side? It looks identical to what we've done, except for that pesky little a and b. That a and b are called the limits of integration. A is the lower limit, B is the upper limit. It's the same thing that you already know A and B as. Where am I starting? Where am I ending? So the thing on the right-hand side of this equation, that guy is simply saying the following. What's the area under the curve of f of x from A to B? That's it. We're going to get to this in a second, but I'll show you a simple example. What's that equal? Maybe it wasn't as easy a question as I
I don't
thought.
get like where the 2 and 0 fall into the equation thing. I get like where they come from.
Okay.
Like what do you do with those numbers?
So what is this saying? This is saying what's the area under the curve of f of x, which in this case is a horizontal line, from 0 to 2. From 0 to 2.
The area is just 2.
Yeah, it's just the area of that rectangle. 2. Okay. Molly?
Will you always be given like the y value of like 1?
You may have to find it. You might be given the more than likely you're going to be given the function x squared plus 3x minus 1. Plug in 0, plug in 2. We'll talk about how to do a definite integral in a second. I just want to make sure you're okay on the concepts. Everybody good? Now you can see how this geometry idea comes into play here. We're going to start by taking functions that give us pretty geometric pictures. Rectangles, triangles, semicircles, that kind of fun stuff. We'll get to that in a second. Okay, so properties. And these are the same, or I don't want to use the word same, similar properties to what we talked about like when we took derivatives. For instance, the definite integral of a sum is the sum of the definite integrals. The integral of a difference is the difference of the integrals. If you have a constant, you can just move it out in front. And I don't want to beat a dead horse here. I think you remember these from when we did derivatives. It's the same property. If you want to take the derivative of 3x squared, you can just take the derivative of x squared and multiply your answer by 3. Now, we didn't do that. We learned quicker methods to multiply the 2 by the 3 and reduce it by 1, do all that other fun stuff. But that's still a property, and that's where it comes from. Why is that equal to 0? Basic.
The distance of the line is 0, or the curve is
Keep going a little bit more. I don't know how clear that is.
that. It starts at the same point where it ends.
So,
It doesn't go anywhere.
so,
The area is 0.
good. How much area is under the curve? Well, we're going from 1 to 1. It has no width. It doesn't matter what shape it is, it has no width, therefore it has no area, and therefore the indefinite integral has to equal 0. Are we okay so far? Okay. We can split an integral into 2 different parts. Now, this one is easier to understand if I draw a picture. What does this say? And again, this is going to burn into your brain eventually. What is the area under the curve from A to B? So it would be this shaded black region. Okay. What is this saying? Well, I'm going to introduce a value somewhere between A and B and just break it into 2 pieces. This plus this. Is that pretty logical? Okay, good. Now, notice the caveat there, C has to be between A and B. It doesn't make any sense if C moves to the left of A or to the right of B. This is a big one. So big, I'm going to get my picture out of the way. Excuse me. When we are doing an indefinite integral, the lower limit of integration has to always be smaller than the upper limit of integration. It's not called the upper because it's on top, it's called the upper because it's a bigger value. In other words, B must always be bigger than A. If it's not, then you can switch it to put the bigger number on top. But when you put the bigger number on top, it has to put a minus, you have to put a minus sign in front of it. It's similar to vectors. If you go in one direction, you're going to have a positive value. If you come back the other direction, you have to put a minus sign in front of it. Okay, so we're going to skip doing the math, and I'm just going to tell you a bunch of information. If I take the cubic function x cubed from 2 to 4, the area under that curve is 60. If I take the line y equals x and I calculate the area under the curve, I'm going to get 6. And if I calculate the area under the curve of the function 1, I'll get an answer of 2. Again, where those come from is not important. What I do want to talk about is how to solve that problem. Now, this is an idea that we can apply that you're really not going to do in the future. When we get to the fundamental theorem of calculus, I'm going to show you a nice, easy way to do this. It's just like I talked about when we took the derivative. You don't really take the derivative and then multiply it by the constant in front. You just bring the exponent down and multiply it by the number in front. Okay? So this can be split into 3 parts. The integral of a sum is the sum of the integrals. 10 is a constant, therefore it can go out in front. 4 is a constant, it can go out in front. 3 is a constant, it can go out in front. Then I plug and chug, and I get my answer. Anything bother you about that? Okay, try and push you towards the correct answer to my question. What is it? Oh boy. Don't stare at the screen, you'll lose your soul. Sucked into the TV set like poltergeist. What does that... Go ahead.
You can finish first.
What does that circled blue thing mean? What am I asking you for when it says evaluate?
What's the area under that from 2 to 4?
Correct. What's the area under that function? What the heck? There we go. What's the area under that cubic? 10 plus 4x minus 3x squared from 2 to 4. Okay? Good. So, what's wrong with that TV? Oh, you don't get the bottom half, sorry. Everybody else good? Yeah. You guys got screwed. Sorry. So, again, my question would be, what bothers you about that? Answer? Negative.
I think it's supposed, it's 3 times. If that's what, you can't have a negative area. Areas can't be negative.
Bingo. Up until this point, in fact, I just talked about it with my geometry kids. If you're calculating an area and you get a negative answer, you screwed up. It makes no sense. How can you have a negative area? Well, this is where things get interesting in calculus. We do have negative areas. So that answer is correct. So, go ahead.
Wait, are we supposed to know how, like, I don't get like how this is done. Like, why was the 10 for that second?
Because I don't know what the antiderivative of that is, but I know what the antiderivative of that is.
So we're just supposed to know that.
Yeah, that's why I said, you'll figure out where those numbers come from later. I was more working towards getting to the negative side. Okay. Well, what is negative area? Okay. Well, again, if you put on a geometry mind, It doesn't make any sense. Because in order to have a negative area, I have to have a negative distance, and I can't have a negative distance unless you're talking about vectors. But you don't use vectors to calculate area. In calculus, that negative area has an exact meaning. It's not as bad as it would initially sound. Area is considered negative if it's below the x-axis. Okay. Any area below the x-axis is considered negative. Which means that cubic we just solved the problem for, a majority of that cubic is below the x-axis, hence the reason we have a negative answer. If you look at the approximation I have in that diagram, my final answer will be negative because the area of the purple regions below the x-axis is bigger than the purple region above the x-axis. Therefore, my final answer will be negative. If the area above the x-axis is bigger than the area below the x-axis, then you have a positive answer. Quick review just to make sure we're all on the same page. Area of a triangle, 1/2 base times height. Yes?
Yes.
Area of a circle, pi r squared. Not 2 pi r, that's circumference. Area of a trapezoid, 1/2 h times b1 plus b2. You might not remember that one. I don't know if there's I'm assuming you know what a rectangle is, right? Base times height. Okay. If you got all that, you're good to go.
Sorry.
Okay? So, here's what we want to do. We're going to start very simply. Start very simply. It would have a lead on the end, wouldn't it? Simply, yeah. That's why I went into math. And we're going to break all these definite integrals into geometric problems. So like when you were doing the rectangle problems with these, you want to just draw yourself a good picture. The rest should be pretty easy, especially if you had a good geometry teacher. So, what is the area under the curve of the function 4 from 1 to 3? First question I would ask you is, what does the graph of y equals 4 look like?
Oh, wait.
Say again?
Horizontal line.
Horizontal line at?
Y equals 4.
Y equals 4. Horizontal line at y equals 4. We want the area from 1 to 3. That. What's the answer?
8. Wait. Yeah.
Why did you second guess yourself?
No one gave me any calculation.
You can't move forward unless you get an affirmation that your answer is correct. Yay, Katie! Great answer! Woo!
Everyone was so silent, so I was like,
It could be that they just don't have a clue.
I don't have a clue.
Okay, thank you for sharing, Molly.
Well, 1 to 3 is 2. And then
1 to
the
3
height
is 2 and the height is 4. No.
That's
Yeah.
one thing.
Good. All right, how about this guy? What's the graph of x plus 2 look like?
Just a line positive, like up 1 over.
What chunk of information, what piece of information are we missing from this problem? Well, first of all, what shape is that? It's a trapezoid, correct. You need 3 things for the trapezoid, base 1, base 2, and the height. What's the height? 3, correct. What's base 1? That's right, you gotta do this. What's base 1?
How is the height 3?
It's a trapezoid on its side,
Oh.
Oh, so
like this.
So then the first base is 2. Oh, we don't know the second.
So h is equal to 3. What's b1?
2.
2. What's b2?
Don't know.
Don't, uh-oh.
5.
5?
Yeah.
Why 5?
Because x plus 2 you put 3 is 5.
Well done. Whoa.
how is it?
Dexter, you may have just caused people to lose their minds. What is going on? Why is it 5?
Two parallel sides and yours.
Oh,
Because,
because you
3
try to see
plus
where
2
that
is
falls
5.
on the line if that's 5.
Where is this point? That point is at 3 comma 5.
I was like, is it a type?
Therefore, this is 5.
How do you
Was that the reaction you were looking for when you answered before? You wanted at least some response from everybody so you didn't think the whole class dropped over dead?
Yeah.
Okay, beautiful.
You just add, like, that's how you explain it.
He plugged 3 into the function. 3 plus 2, 5. Yeah. Okay, questions so far before I erase this one?
Yeah, I.
Okay, one more for you. Oh boy. What does that function look like?
It starts at negative 4. Wait, x move.
How'd you get semicircle? Isn't that what
They like go.
you're definitely
Oh.
right. I just don't know how you got
Yeah,
that.
when you it's not either. It's just to the left forward. It's positive.
Okay, I'll ask my question again. What does that function look like?
It's a semicircle. I'm actually.
Or it doesn't.
It's a what? Kinda. It's a semicircle. Very good. Is that semicircle the, I don't know why I'm looking over there. Is the semicircle the top, the bottom, the left, or the right of the semicircle, of the circle? Not a bad guess. Question for the rest of you, why would left or right side of the circle be an absurd answer?
Because that's not a function.
Bingo. Thank you, Lily. Good. Back to you. Bottom? What makes you think it's on the bottom? Okay, so let's talk about why it's at the top. Because semicircles show up a lot, I want to go through this derivation. What are we saying weird?
You said trapezoid and
You said
trapezoid and derivation. Is that how you say it?
Trapezoid.
What is that? That's not trapezoid.
It's just a chord.
Trapezoid.
You are the only person I've ever heard
What's
pronounce
another
it
thing you
that
say
way.
weird?
Yeah, that's it.
He says something else weird.
No.
Trapezoid.
Trapezoid. That would be trapezoid. This is a trapezoid.
Trapezoid. Like,
I feel like
physically uncomfortable. It's okay, if you can say trapezoid.
How have you all learned to pronounce this?
Trapezoid. It's like pecan and pecan.
No, it's not. It's
No, it's not. It's trapezoid. It's not like dog and dog.
Potato, potato.
Okay.
cat and
Trapezoid. You can clearly hear it. Trapezoid. I don't know what's wrong. Okay, so we come back to this guy. This is not a function. What is that? No, sorry, this. That's a full circle with a radius of 2. Very good. Now, if I solve this for y, I get y squared is equal to 4 minus x squared, so y is equal to, whoops, y is equal to plus or minus the square root of 4 minus x squared.
So,
Okay, when you take the positive, you get the top half. When you take the negative, you get the bottom half. Everybody with me?
yeah.
Okay, now I'll show you the other one, even though we'll never deal with it. And that would be if I do x squared is equal to 4 minus y squared. So x is equal to plus or minus the square root of 4 minus y squared. Positive is the right half, negative is the left half. But again, we're dealing only with functions, so that shouldn't be relevant to us.
so you don't look underneath the root, you look in front of it.
Correct. It's always going to be minus when it's a semicircle. All right, now let's get back to calculus. That having been said, what's that equal to? All right, fine, I'll draw a picture for you.
trapezoid?
I think.
Eric, what's the answer?
It's pi r squared over 2, and r is 2.
What?
Continue with the logical progression, please.
It's 4. Wait, no, wait. Hold on, that's the true number into my mind.
Oh, it's just a
Yeah.
4, 2 pi.
4 2 pi?
2 pi.
You sound like Shakespeare. 4 2 pi, lest I be 2 pi? That is the question. Whether it be noble in the minds of men to suffer the calculus of.
2 pi.
He's dead.
2 pi.
He's dead. Him and Biggie are on an island together.
Those pies. It's too high.
Look at you getting all international. Did you say dos pios?
with the center.
Well, we never would have known.
The radius is 2, because
It's French.
the
How do you
thing
say
that's equal
2
to is
Okay, so-
2r. So the circle's like center, x minus the center of the square is
There's our rectangle.
y minus
There's our
the center
trapezoid.
equals 2r.
There's our side.
Is the answer 2
Yeah, so this is 2 times
2
the
pi.
radius. So the radius is 2.
How do you get there from there? Okay.
For that, you solve for y, and then
Okay,
the
how about
constant
this
is
guy?
half. This is just if you solve the equation.
Now, one of the interesting things about this problem is that I'm not going to, nor are we ever going to talk about how to take the antiderivative of absolute value, just like we will never talk about how to take the derivative of absolute value. It always involves drawing a picture. When we took the derivative of absolute value, we always drew a picture, figured out where it was, and went from there. The same thing is true here. Let's draw a picture. I happen to have one right here.
It's a V.
Very good. It's a V. It would have been too easy if I would have said from -2 to 2, so I changed it to go from -3 to 2. I have 2 rectangles. Sorry. I have 2 triangles. It's amazing they let me teach geometry. I have 2 triangles, a magenta one and an ugly brown one. Can you find the area of those triangles? Yeah. Done.
He's got the
Actually,
So really long. It's 6.5.
Are we good?
no.
What's the matter?
I
Are you okay with the picture?
Yeah, I understand the picture, but I don't know what.
So I know that this is too wide.
Yeah.
What we're missing is this. So remember on the one that Dexter helped us with, we found that point by plugging it into the function. If I plug 2 into the function, I get 2. If I plug -3 into the function, I get 3. That makes this 3, this 3, this 2, and that 2. 1/2 base times height is 4.5, 1/2 base times height is 2, and amount.
And then it's like, so you're
We're all done.
and then it's like the, you look at scuba, and then shimmy, and then crank.
Okay, so one of the problems that we've run into so far is that this works great if your functions turn out to make a nice, pretty geometric shape. If it does happen to give you a triangle, a rectangle, a trapezoid, a semicircle, well, what happens when it doesn't? How are we going to find the definite integral of something like a cubic function that isn't going to generate a nice, pretty geometric shape? That's good.
We use geometry stuff like the tan and secant.
Nope. We actually have a process which is called the fundamental theorem of calculus, which we'll get to later.